Awesome. So we are talking about centripetal forces, and also the other thing that we also have to just sort of remind ourselves is linear. In linear motion, obviously we are all aware that in linear motion, we say that force is equals to ma, and that is from which law of motion is that? Anyone to help us? Is it the first law or the second law or the third law? From which law of motion does it state that force, a resultant force produces acceleration in an object? Which law of motion is that? Newton's laws of motion. Okay, so I'm going.
The second law.
Awesome. That is correct. So the second law of motion, Newton's second law of motion states that the resultant force produces acceleration in a mass. Of course, I'm paraphrasing it. It states it in a different way. But from that same concept, so as long as we are dealing with a force, whether it's centripetal or it has a nickname of whatnot, if it is a resultant force, that force will always produce acceleration, whether it's the force of gravity or centripetal force or whatever weird name we can give it. A force will always produce max acceleration in an object if it is resultant. Of course, if it is being opposed by another force, then the net force will be zero. But if there be a resultant force, it will always produce acceleration. So, and this is also the case with rotational motion. Even in rotational motion, when we have a centripetal force, all right, this centripetal force will always produce acceleration. Now, this type of acceleration which it will produce will be called centripetal acceleration. And then how do we describe this acceleration? We describe it as v squared over r. This is when we use linear velocity. Linear velocity. If we wanted to use angular velocity, we would call this centripetal acceleration as r omega squared. So this is how it is stated in using angular velocity. It is r omega squared. Now, when we have an acceleration of that type, and then we have that force with the m as a constant, we can write our equation like this to describe the effect of centripetal force. So now let's look at a diagram that can just help us understand and appreciate this concept. And so the car shown below is moving, of course, in a circular path. Obviously, I'm sure you have seen a car move around a roundabout. Usually, a roundabout, if you are moving in a roundabout, especially if the driver is moving at a considerably, considerable speed, as it to be curving. I hope you are seeing my hand, as it to be curving like that, curving like that, you will always feel pushed in that direction. All right. So if you are sitting on the seat, you always feel like you are being pushed towards the window side. So you discover that the car is moving like that, but you are always being pushed perpendicular to the component of your velocity. So the component of your velocity perpendicular to it, you always feel a certain force. And the only reason why a car doesn't spin out of control or slide away is because we expect the tires to have some grip on the tarmac or on the road. So again, we have to see a free body diagram, because obviously a free body diagram gives more meaning to what is being felt or what is experienced. So we know that due to the weight, all right, due to the weight of the car, for example, since we have looked at an example of a car, due to the weight of a car, we expect there to be weight pulling the car down. But since the car is not, accelerating downward, it's not going below the ground, it's on the surface of the road, there's another force, normal force, upward. All right. So with that normal force, of course, we can use it to calculate the friction force. The friction force will be in this direction, and then the centripetal force will be in that direction. All right. Centripetal force will always be in that direction. And if the friction force, if the centripetal force is equals to the friction force, this is the static friction force, then we have our centripetal, we'll have no motion in the x-axis, but of course we'll have our centripetal acceleration because our centripetal force acceleration is in that path, but of course we'll have no motion in the x-axis. All right, so when we continue, like one thing I can always advise you is that when you are dealing with motion involving forces, whenever you have a force anywhere, even if they have not indicated it to say, okay, that's a force, if you can perceive that there's a force here happening, always sum your forces. Of course, usually the best thing is to sum your forces in the y-axis first, and then after that you sum your forces in the x-axis. Always do a summation of forces in the x-axis and summation of forces in the y-axis, all right, and see what happens. So usually, in most usual cases, you find that summation of forces in the y-axis is usually 0. That is for a balanced system in the y-axis, but in the x-axis, usually there is some movement. So you find that summation of forces in the x-axis is equals to MA. But if there's no movement also in the x-axis, then summation indeed of forces in the x-axis is also equal to 0. So please, whenever you are dealing with questions involving forces, even if they have not stated that there is a force here, always sum your forces in there. Sum your forces, do a summation of forces, indicate it even. Don't sum it, don't do it in your head. And you discover that, especially the reason why I said sum your forces in the y-axis first is because in the y-axis, usually that's where we encounter the normal, all right, the normal force. You have to determine your normal force first before you can even find your friction force. So therefore, you can't do your friction force, your summation of forces in the x-axis first, because usually if there's a friction force in the x-axis, you will not be able to determine it unless you have an expression for the normal force. All right. So with the case that we have seen, in this case, if we sum forces in the y-axis, how many forces do we have? We only have the normal force pointing upward, so it will have a positive sign, and we have also the weight pointing downward. But sometimes you may find that there's another force which is at an angle. All right, that is sometimes. If there's another force which is at an angle, then you need to make sure that you also put this force, because this force will also have a y component. All right, but in this case, we only have a simple scenario where we only have two forces, one pointing up and one pointing downward. So obviously, it makes our work easy. So we sum our forces in the y-axis, we get our expression for normal. All right, and then I should have indicated here as x-axis. All right, so I'm sure you're able to see we have normal minus mg is pointing downward. From there, we can get our expression for normal. And by the way, normal force is not always equal to mg. All right, some people may think that normal force is always equal to mg. No, normal force is equal to whatever it is equal to. Sometimes it may even be equal to 0, meaning there's no normal force. Sometimes it may be equal to something. So when you are when you are doing your solutions should be able to tell you what your normal force is equal to, not always predicting that, oh no, the sir said, in fact, I'm not a sir, I'm still a student, as you can see. So yeah, anyway, in fact, for some of you guys who don't know me, my name is Albert. So you say Albert said that normal force is always equal to mg, but that's not the case. It is only equal to mg when we have solved it as equal to mg. Are we following? I've been talking a lot. Are we following?
Yes, sir.
Oh. Yes, sir. Yes.
Awesome. Mm-hmm.
Yes.
Thank you for following. So forces in the x-axis, as you can see, in the x-axis we have the friction force pointing in the negative direction and the centripetal force pointing in the positive direction. That is how come we have this expression, and we have it that our centripetal force is equals to friction force. And we remember we said that our centripetal force is equals to V squared over R. And then our friction force, since our friction force is equals to normal, we know that our friction force is equals to normal mu normal, all right? And our normal is this, mg, and our mu is our coefficient of friction, coefficient of static friction. I'm sure when we looked at forces, laws of motion, we looked at friction. We are already past that. So this is how we have replaced. For the normal, we have put mg and mu there. And then we have seen that we don't even need to know what our mass is. We can even cancel the m there, and then cancel also the m there. And then we can even solve. Even if we have been taught to say us to find the value of mu s, we can even manipulate this equation to get our mu s is equals to V squared over Rg. So this is a very important equation. Okay, so yeah, we are going to look at questions very soon. I just wanted you guys to also just get the foundation of what we're looking at. Like I was telling your friend who came earlier on, I told him that it's better I spend the whole time teaching you how to solve a fish, to catch a fish, all right? Teaching you how to catch a fish than giving you a fish, because solving for you a question is like just giving you a fish. Okay, there you have a fish, eat. What about when you feel hungry again? You want more again, right? But here I'm teaching you the techniques of how to catch a fish so that even when you are hungry and you are on your own, you not say, where is Albert? You just say, okay, Albert taught me how to catch a fish. And there I go with my net or my hook. So we have, what's this? A diagram here. In a case where, here we had a situation whereby it's on the level field, all right? It's moving in a circular path, but on a level field. But what about if it is moving in a circular path? Obviously, this car will be moving like that, but on what we call banked, all right? Banked road, all right? So this is what we call a banked road, and you guys should be familiar with these things, because even when you go into society, people will be talking about, wow, I was traveling at 120 kilometers per hour on this banked road just before you reach Chipata, Lundazi, whatever. You'll be thinking banked. Did they take the road to the bank or something? No. When someone talks about the banked road, meaning the road has been put at an angle. Usually, if a road is on the surface like this, the challenge is it is able to slip if the car, for example, if it is raining and it's moving at a high speed, it's trying to rotate through a corner. The car, you find that it is skidding. But if we bend it like that, the car will not easily slip away like that because gravity will be also pulling it down. So in a case where we have a car, for example, moving in a banked road. Okay. So we have also Precious there. We can see you. Precious, we can see you. Yeah, so when we look at a banked road, we also see that there are certain forces that play. And these forces that play, we can also introduce an axis like this, all right, a rotated axis. All right, a rotated axis like that. And call this one our x-axis, and call this one our y-axis. So if we have a situation where we have a banked road like this, and we have been given an angle with respect to the horizontal, all right, we expect that the weight of the car, which is mg, is always pointing downward. I'm sure we know that the weight of the car is always pointing downward. But again, we also have a scenario where we have the component of the weight along this banked surface. Right? We expect that this surface will have a component of weight again along it. Are we following? Are we there? Maybe I've lost you in my talking, so it's important for me to know that you are following. Are you following?
Yes. Yes.
Yes.
Awesome. Okay. So since you are following, I will explain. But usually, I'm sure we all know how these forces play. But in a case of just for the sake of explaining, I will explain that. If we have our rotated axis, I'm sure we are usually used to having our x-axis just the way it is, perpendicular like that, you know, y there and our x-axis there. But we can also rotate it, as we can see. If the surface we're looking at has rotated, we can also rotate our Cartesian plane, such that even here we will need to do summation of forces in the y-axis, and as well summation of forces in the x-axis. All right, so we have weight having a component of it in the x-axis, and it also has a component of it in the y-axis. And in this y-axis, we have the normal force, which is just pointing upward at no angle. But again, since the car is moving like this, and centripetal force is always trying to move also a car in that direction. All right. So centripetal force is trying to move a car in that direction. And then the weight of the car, the component of the weight of the car, is trying to move the car in that direction. And then some of our friends are as well asked to say, why do we have sine theta in the y-axis? I mean, this is x-axis, by the way, but we have the component of the mass of the weight as mg sine theta. It's because look at this angle where it is. this angle is adjacent to the y-axis. So if we want the component of this weight with respect to the x-axis, then it will be opposite of this angle. All right, the x-axis is opposite to this angle. All right, because if I can draw something parallel like that, if I can draw something parallel like that, it is in the same line with this x-axis. Therefore, the x-axis is indeed opposite to this angle. No wonder we are using the sine function. All right, because of where the angle is being taken. This angle is always equal to this angle. All right, our centripetal force is always pushing us away from the rod. And we also have our friction force pushing us in this direction. Our friction force changes direction depending on where you have the largest force. So you will find that the weight, the component of the weight is usually large. Therefore, the friction force would be pointing this side. But if the centripetal force was large, friction force was going to point this side. For some of our friends who may want more information about how friction force changes its direction, you can inbox me so that I can explain more. But today we are not concerned about just talking about friction force. We are trying to describe an object moving in a circular path. Are we together so far?
Yes. Yes.
Okay, I think I don't only have two people. I have quite a number. What did the others say?
Sir, can you just do a quick summary? I was kind of disturbed by some people.
Okay, the quick summary will be on the next page when we look at the equations. All right, so the quick summary is that when we have an object, a car, for example, moving on a banked road is a road which is put at an angle. All right, we will have since we have a road which is at an angle, obviously then we also need to rotate our axis. Have you seen our Cartesian plane is rotated so that it can accommodate what is happening here? All right, so therefore we'll have forces in the y-axis along this. This is our y-axis and this will be our x-axis, not this one, but this type of axis which is rotated. Our x-axis is that direction, our y-axis is that direction. So what are these forces that are there? When we look at forces in the x-axis, forces in the y-axis, we see that in the y-axis, this car is not moving. Remember I said that this is the y-axis. All right, so in the y-axis, this car is not moving this way or that way. So our summation of forces in the y-axis is equals to 0. What forces do we have in the y-axis? In the y-axis, we have our normal force, all right? Our normal force. Okay. We have our normal force like that. But again, the other thing that you have to realize again is that when you want to choose an axis, all right, when you want to choose an axis, whether to use your x-axis, which is like this, or to use your axis, which is just the normal way. This is your y and this is your x. Whether you want to just use your Cartesian plane like this or your Cartesian plane like that, which is like that, your y-axis rotated like that and your x-axis rotated like that. One thing that you have to, it's all due to convenience sake. There is no norm in physics that says my Cartesian plane has to be this way or that way or this way. It is your choice, all right? Man has chosen to say, okay, this is what I will use because it is convenient for me, all right? This one eats breakfast at 6 hours. This one eats at 10 hours. There's no norm that says breakfast should be eaten at this hour. It just says, okay, you should have some breakfast, at least. So that is just an analogy that I wanted to bring out. So even here where we have a case where we have, in a case where we have a rotated axis like this, a rotated plane like that, where we have our car, which is there on that banked road, it's moving in a circular path, but we can't show it properly here. We'll just show this part. So if I want, I can still use my normal, because it's at this angle here. It's at this angle. If I want, I can still use my normal Cartesian plane, this one being my y, and this one being my x. Now, in this case, what I'll do, remember, my normal force is always pointing in that direction. My normal force, and there's an angle here. Obviously, you can see that there's an angle, and I always say that this angle is equal to that angle, all right? So we have our weight pointing us in that direction. Also, in fact, we also have our weight of the car or whatever object it is pointing us this direction. We have our friction force, and also we have our centripetal force pointing us in that direction. So if we want, all right, we can use this same Cartesian plane because it is convenient for us. All right, if we use this Cartesian plane, what will happen to our equation? What will happen to our equation is that when I sum forces in the x-axis, I'll have you seen my normal force? My normal force, to get its component in the y-axis, what will I do? Since there's an angle here, I'll do normal force cos this angle, I'll get the component in the y-axis. And mind you, it's pointing upward, so it will have this expression, all right? And then for my weight, I'll just say that my weight will just be, since it is straight along the y-axis, along the negative y-axis, I'll have a negative there, all right? And since there's no movement also in the y-axis, everything is equated to 0, all right? So therefore, making n the subject of the formula, I'll have my n cos theta is equal to mg, and therefore this expression can be derived. We also go in the x-axis and say that since we don't want the car to be sliding down or upward, we don't want the car to be sliding, we just want it to move across that circular path properly. We don't want it to slip away or skid down. We just want it to make that curve properly. So even as I'm talking, you should be able to imagine what is happening. Okay. So what forces do we have in the x-axis? In the x-axis, we have, this is our x-axis, mind you, this is our x-axis. Our x-axis is like that. So what do we have in the x-axis? We have our normal force. Our normal force, since we have it at this, at an angle, meaning it will also have some component in the x-axis, all right? So since it is at an angle, it will have some component in the x-axis, and some component in the y-axis is what we saw here. So its component in the x-axis, it will be, since the x-axis is opposite to this angle, since the x-axis is opposite to this angle, it will be n sine theta, n sine theta. Therefore, we have n sine theta here. In fact, I've already even just equated them, but would have seen that our centripetal force